All right, this is going to be the beginning of the 7B1 video. I actually have part of the video that covers a good portion of this section, so we're just going to need to set some groundwork for the before of that. So we're going to be talking about, and if you kind of remember, we had the problems from the previous section 7A4. Now I'm going to make this one just a little bit easier, just as a comparison. So say we had a mean, let's say women's height. I'm going to make it a nice even number of inches. Let's say it was 64 inches. So the mean of women's height, 64 inches. And let's say our standard deviation is 2 inches. Again, those aren't exact values for any kind of study. It's just to make the numbers work out nice here so that we can talk about why this next section is important. So when we learned this in 7A4, we learned that you add the standard deviation 3 times. So that gives me 66, 68, 70. We can subtract it 3 times from the mean. So that'd be 62, 60, and 58. And we learned the empirical rule. We said that if you go one standard deviation on either side. So if your mean 64, that'd be then from 62 to 66. We said that was 95% of women would be in that height range. Not sorry, 95. That would be 68%. So let me draw that in. So 68% from the 62 to 66. Okay. And then we said, okay, if you go 2 standard deviations, this is the one my brain was trying to do. So that'd be 60 to 68. That would be 95% of women's heights. And then if we went the 58 to the 70, the third standard deviation, that would be the 99.7. So that was our empirical rule. The problem with this is there could be a woman out there who actually has a height of 67 inches. That's not one of our numbers down here at the bottom of this value because our mean was 64, standard deviation was 2. We don't get 60, 67 exactly. We know it's about halfway between 66 and 68, but how do we know what percentage that mark would be at? What would be below it? What would be above it? That is the reason why we standardize our raw data into what we call the standard normal curve. So our goal in this section is that we're going to have this bell curve, and instead of having the raw data down here, our mean will always be centered at 0. And then when we go standard deviations above or below that, we're going to move by units of 1. So 1 is 1 standard deviation above, 2 would be 2 standard deviations above since it's positive, and then 3 would be 3 standard deviations above. Then we'll have a -1, -2. Again, these are all standard deviations below the mean, and a -3. So we're going to essentially try and get a formula, which we're going to call our z-score formula in just a minute, that takes raw data. So you're going to take a particular item. So say that person who is 67 inches tall, we'll subtract the mean from that, which would be 64, and then we'll divide it by the spread from the mean, which is the standard deviation, which would be dividing it by 2. And that will give us a position on this, what we call standard normal curve. And the beauty of this is once we get this standard normal curve, we have a table with all of the varieties of numbers that we can think of up to 2 decimal places between -3 and 3. We'll be able to say, oh, someone who is 67 inches corresponds to this specific z-score. We'll look that up in the table. The table will always tell us what percentage of people are to the left of our specific z-score. And if we want to know what percentage would be to the right, we'll just subtract from 100% or from 1, since all the table values will be decimals, but those can be turned into percentages. We've learned how to do that. So this really is the big thing, is that when we had the empirical rule, we can only really talk about specific standard deviations away from our mean. By standardizing any raw set of data with a mean and a standard deviation and a particular score or value, we will be able to find its location on this standardized curve that goes from -3 to 3. It does possibly have outside values of that. Remember, you can have outliers. And then we'll be able to say, okay, let's go to our chart, our Z chart, and figure out that probability or percentage if you want to turn it into a percent. Okay. So the normal distribution, which we said was continuous, is most important and widely used distribution in statistics. It's a bell curve shaped. We learned, this is all stuff we learned in 7A4. The total area under the curve is 1. It's symmetric around its mean, which we also learned the mean is also the median and the mode. The area under the curve is equal to 1. Denser in the center means more area or more percentage towards the center, less in the tails. And then we learned that we can figure out how to label this based on its mean and its standard deviation. And then this last one is just restating the empirical rule we learned. So we learned that standard deviation, remember, is a measure of the variation or dispersion, that means spread, of a set of values. A low standard deviation indicates that the values tend to be close to the mean. We call that also sometimes expected value. These are just other words in case you ever hear those phrases. While a high standard deviation indicates that the values are spread out over a wider range. We've already learned how to do the 68, 95, and 99 point rule. So that was part of the 7A4. So now we're going to talk about that Z-score. This is taking our raw data, like the 64 inches and the 2 inches of standard deviation, and turning it into the scale of -3 to 3, okay? So the Z-score, which is a position score, that's all it really is, tells you how many standard deviations of value or a specific data point is either above if it's positive, or if it's a negative value when you do it, below the mean. If your Z-score is -1.5 when you use the formula we're going to teach you, then that means that the Z is -1.5, but the value, if you write it as a sentence, you would say that's 1.5 standard deviations below the mean. Whereas if your Z-score, when you work out the formula, comes out to something like 2.25, that should have a no 5 on it. It's a typo. Say it's just 2.2, then the Z-score is 2.2. The value is 2.2 standard deviations above the mean because this one's positive, okay? The Z-score comes out to 0, means you're at the mean. 0 would be the actual mean when we standardize. So if a Z-score comes out positive, your value you're looking at is greater than your mean or to the right of your mean. When your Z-score comes out negative, the value is less than the mean or below it, okay? When it's 0, you're actually looking at the actual mean. So this is the formula that we need to know how to use. Okay, so to find a Z-score of a data value, we'll subtract. Now this is very important. This is the item in question. This is a specific item that you're going to be asked about. For example, you could say how many or what, percentage of women are taller than 67 inches. So 67 is a specific item. This is your mean that they gave you. That's the average for all of the women. And then this is the spread of the data or this around the mean, which is the standard deviation. Okay. So your specific item minus your mean divided by your standard deviation gives you your position score. So let's try converting one of these. Okay. So we have the birth weights of infants born full term in the US have a normal distribution. That's important. Otherwise, you can't do a Z-score with a mean of 7.7 pounds. So that's my mean, standard deviation of 0.85. So those are both the mu and the sigma. Those are the symbols for mean and standard deviation in a population. What is the Z-score of an infant that was born full term in the US that weighed 8.5? So this is my X. This is my specific child that I'm comparing to all of the other children in the world, okay, that were born in the US. So Z equals the specific weight of the child in question minus the average weight of all those babies divided by the standard deviation or spread of those weights from the mean. So then we're going to take our calculator and we'll do, let me make sure I'm doing a full screen share so you can see the calculator. I'm not yet, so let me do that. So we're going to do 8.5 minus 7.7. So that'd be 0.8 on top. We're going to divide that by 0.85. And notice that gives me a Z-score. And we usually go to Z-scores only of 2 decimal places. So this would be approximately 0.94. So not quite 1 standard deviation above the mean, just a little bit below that. So if you think about where we're at on the standardized curve, we've got our 0, we've got our 1. That baby, that specific baby, is right about here, okay? That would be our 0.94. So we found the location or position that child's weight ranks amongst the entire population of US born babies, full term, okay? Now, why that's important is going to be this next part. So we're actually going to jump to how do you read the table that goes with this in just a second, because I actually did a lot of the similar ones on the video. And when I taught this in class before, the video that kind of tied in with that, because it's one I did in a previous semester, we did at least one of the 2 things. We learned how to find the Z-score in class, and then we also learned how to read the table. So this is how you find a Z-score. You take your specific item minus the mean they gave you, divide by the standard deviation. That gives you your position on the standard bell curve that goes from -3 to 3. Okay. So that's where our child, baby, infant is. That's where their position would be for their weight. Okay. So again, we know that's more than 50% that would be smaller than them, babies, because if you're at the halfway point, 50% of the babies would be left of your weight, 50% would be to the right. So this is definitely going to be an area more than 50% if we're thinking about it as a percentage. But we want to have a nice, accurate estimate for that. So that's where the table comes in. So like I said, some of these I'm skipping over. It's because they're in the video that's going to be posted right after this one. So how do we use the z-score? So if you have your formula sheet, you could look at that. In fact, let me see if I can pull it up. Let me pause my share real quick. Because we do have sometimes the big table on the formula sheet. We might have discontinued it because then I'll tell you why. Newton, every time you have a z-score chart problem, they give you a zoomed in version of the z-table to use that is specific for your problem. It'll have more than just your answer on it, but it's like we zoom the table in to what you need. But there is a huge table. The table that we read for z charts is actually a ton of values between essentially a little more than negative or a little less than -3 all the way up to a little more than +3. So it is something that I always find, and yeah, it's not in the formula sheet anymore. And the reason for that, I just wanted to double check, is because it's provided in every question. So let me pull up just a version of it online and I'll share that instead, just so you can see what it kind of looks like, even though you're not going to have this specific one. Okay. So let me resume my share, make sure it's sharing that. Yep. Okay. So again, you don't need to know how to read this whole entire table because you're going to get zoomed in versions of it for each question that they ask you. But essentially, like this one, I just Googled one. This one had, it goes all the way down to -3.6 because remember, if you're at -3, there's still like 0.15% of the data below that. We learned that with the empirical rule. But you'll notice, here's how you read a Z table. You have your first number, your ones place number for your Z-score, and then you have your decimal, and then you have your tenths place. So if your Z-score is, say, 1.56, again, right now, this is all the negatives, so we'd have to go to the second page. Those are all the positives. So I'd go down to 1.5, and then I have to find the 6 in the columns, their hundredths place. So here's 0.06. So if you follow 1.5 over until it lines up with the column of 0.06, you'll see that that's 0.9406. Now, what does that mean? That is always the area below your z-score, below the position that you're at. So if you're at 1.56, 94.06%, because this is right now in decimal form, this is a probability. If you times that by 100, it changes it to a percent. So that'd be 94.06%. Now, a lot of times when you're doing these in Newton, they're just going to ask you to leave it in decimal form. But like the context is that's technically 94%. Okay. So we would be saying, oh, if I have a z-score of 1.56, 94% of the people or, babies or whatever it is we're measuring, their weights, their heights, they would be less than me. Okay. The opposite of that is they could be greater than, right? To do greater than, you have to remember that a whole probability is 1, right? For 100% and a decimal, that would be 1. So 1 minus this decimal form would give you the probability that you are greater than that position, okay? So I do have that in the note. I just wanted to talk about it by looking at a full table. So it says probabilities that can be found using the empirical rule, remember, are nice ones, the ones we get when we get the adding and subtracting the standard deviation on our graph. If that doesn't work, if the data value we're looking for is in between some of those, we will convert to a z-score and then use the chart, okay? So I wrote some notes here. The chart is only going to provide the probabilities to the left. So if this is my specific item, if I convert this to a z-score, then I'm only going to be able to find the area to the left when I read it in the chart. Okay, so if to find the probability of the left, you just find the probability corresponding to the z-score. So you have to convert your x to a z-score and then find the decimal form of that probability. That exact number in the table is always the left area, to the less than side. If you need to find the probability to the right, which means greater than, taller, higher, more, heavier, longer lasting, whatever, that means to the right, greater, then you do the area of the whole curve, which is 1, which we know in a percent, that would be 100%, but we're going to leave it as a 1 because the table reads in decimal form. We would do 1 minus the chart probability. So that's how you do your to the right. So this is the area to the right. To the left, you literally just look it up in the table. That's all you have to do. Okay. So I wanted to do one of these together, and it's actually number 7 and 8. And then the rest of this is in the video that I'm going to be posting. So how do we read the Z-chart probability table? So it says the left column, we already talked about this, shows the 1 and the 10th digit. And this is how it's going to look on your homework. They just zoom in to a portion of the table that has the required Z-score that you need. It won't tell, it won't have just that one value. You still have to read it. And then the top row shows us the 100th digit. So to find the probability given a Z-score, or if you convert to a Z-score first and then find the probability, you will find the row corresponding to the 1s and 10th digit of your Z-score, then trace over till you find the correct 100th place. And then that probability there will be the area to the left. Remember, less than. If you're looking for the area to the right or the probability to the right, you need to do 1 minus the answer you get. So I've got both right here. So we're going to find the probability, which means we're going to stay in decimal form, not go to percentage, to the left for a Z-score of 1.26. So here's 1.2. The 100th place is 0.06. Follow those over till they actually match with a value, which is right here. And since this is left, your answer is the actual exact decimal. Okay. So roughly almost 90% of the data would be to the left. Now, visually, what that means is if you have your Z-score of 0 and you have your standard deviations 1, 2, and 3, 1 is right here, and then 0.26 would probably be a little bit past that, and then we're doing all the area to the left of that. So we're saying, essentially, if this is 1.26, it's kind of hard to write that in there, then that area to the left of that is almost 90% of your bell curve. Okay. Find the probability of the right for a Z-score of 1.32. Okay, so 1.3, then the 100th place is 2, so that'd be 0.02. Notice that this is not going to be correct for our final answer. Area to the right, if we're looking at this, so it's 0, 1, 2. So here's about 1.32. Again, it's not much further than what we were doing on the last one. I'm just estimating where 1.32 might be. We want the area to the right, okay? Notice that's not even more than 50%. 50% would be, half of the bell curve. So if you look here, that's very misleading if you don't remember how to read the chart, because this is 90%. That's definitely not 90%, because like I said, it's not even half of the bell curve, so it's definitely less than 50%. What we do when we're going to the right is we do 1 minus the decimal, because the decimal is to the left, not to the right. And probability adds to 1 for 100%. So if we subtract this, we'll get 1 minus 0.9066. It's 0.0934. So almost, not quite 10%, it's about 9.34% of the data would be to the right. Now, again, my tail is a little too high here. I'm horrible at drawing bell curves. Think about shading more of this one. That might be more visually, like if you had 1.32 marked and you shaded this way. But remember, it's 2 ways to read it, essentially. If you're going to the left, you just get the number. If you're going to the right, it's the opposite direction. So it's 1 minus that. Okay. And then the rest of my examples for this notes were already done in a done video from another section that I had taught in the past. It's all the same problems. So I will be posting that right after this one as well. All right. Have a wonderful day.